There we go. All right. And let me hand things over to group 6 to present their heliostat.
All right, you guys ready?
I'm ready.
All right. Good afternoon, everybody, and welcome to Group 6's presentation of our design, the Reflectile. This unique name stems from the combination of the biological class of our mascot, Reptile, and the reflective function of a heliostat. Our group is made up of Nicholas Belanger, Ricardo Garcia, Mu He, Kyle Karmahalis, Jonathan Mitzenmacher, and Zihong Ye.
The focal point of our design is our hedgehog concept. The universal joint. A universal joint allows for a unique, new, and efficient design while also keeping the cost inexpensive for such a pivotal piece of the puzzle. The design implements these values throughout, allowing for the ability to keep the overall heliostat module cost less than the majority of our competition. As we soar through the rest of our presentation, please continue to reflect on this statement. As one of my past professors once roughly stated, a great design minimizes parts. Our heliostat module consists of 4 mirrors that can move independently. The mirrors are placed in parallel on the base structure in a square arrangement. 8 servos are controlled by an ESP32. The width of the heliostat is 1.345 meters, and the height of the heliostat is 0.265 meters. We did not include the height of the concrete because the concrete will be buried below the ground. Our design has 1 square meter of total reflective area with a module area of 1.81 meters squared.
The panel assembly of our design uses Mylar as reflective material. Mylar film is glued to acrylic sheet using epoxy resin. The acrylic sheets will support and protect the Mylar film. This design ensures an optical efficiency of 77% while achieving lightweight and low cost. The panel mounting plate uses a buckle design to hold the acrylic, so we don't have to use tools for installation or uninstallation during the maintenance. The panel mounting rod is used to connect the universal joint, which we will talk about in the rotational mechanism subsystem. Our panel assembly fully considers our customer needs at the beginning of a design and quantifies them to ensure that all needs can be met. Overall, our panel assembly design achieves the goals in panel number, optical loss, cleaning ability, input thermal power, solar concentration ratio, and heliostat placement range.
The purpose of the panel assembly is to concentrate enough solar energy onto the receiver tower. So in our design, we assume the average solar flux in Las Vegas to be 174.3 watts per square meters. Considering that our reflective panel has a 77% optical efficiency, after calculation, we can know that our design needs about 7,500 heliostat module to meet the required thermal power input and solar concentration ratio. Considering the functional work between each heliostat module, the operational area of each module will be about 3 square meters. After calculation, all modules will have a total area of 21,420 square meters. Considering the sun angle change in Las Vegas during the winter and the summer, we decided to place the heliostat module in a circle as close as possible to the receiver tower. In the end, our placement radius is 82.6 meters, which is smaller than the requirement of 100 meters. Within this area, the heliostat module will not be shaped by itself. Also, smaller placement space means easier maintenance and control. The maximum wind speed in Las Vegas can reach 90 miles per hour, which is 40 meters per second. Therefore, in this design, it is necessary to consider the bending stress when the panel is blown by the wind. And we need to determine if it will cause failure. Due to the unique design of our panel, the acrylic sheet will be wider than the panel mounting plate at the bottom. Therefore, the maximum bending stress of panel assembly is located at the edge between the acrylic sheet and the panel mounting plate. Our design uses a 2 mm thick acrylic sheet. After calculation, the winds can cause a force of 258 newtons to the entire panel. At this time, the maximum bending stress is 29.5 megapascal. So our factor of safety is 3.075, which satisfies the customer needs. In addition to the bending stress, since the panel will be exposed under the sunlight most of the time, the heat resistance of the panel also needs to be analyzed. Under direct sunlight, the optical loss from the panel will become the heat energy absorbed by the acrylic sheet. At the same time, the panel will dissipate heat in the form of conduction to the surrounding air. When the panel reaches the highest temperature, the heat transfer of panel will be in steady state. So the maximum temperature of the panel can be calculated by the following equation. In this calculation, we assume air thermal conductivity to be 27.37 watts per meter Kelvin. In this case, the panel will reach a maximum temperature of 55.62 degrees, which is lower than the temperature limit for acrylic panel. Therefore, this design can meet the thermal resistance requirement.
Reflectile's mounting and rotational system focuses on modularity and controllability. Each rotational mechanism can rotate independently on two axes, meaning that any panel can be rotated at any angle independently without interference. This is one of the methods our group used to reduce optical losses during solar tracking. Through the employment of 3 universal joints, this design can achieve a maximum rotation range of plus or minus 60 degrees in any direction. The larger universal joint serves as the pivot location, while the servo motors transit their rotational forces through the push rods to the smaller universal joints. This subsystem is supported by CPVC in order to withstand the loads from the panel assembly, as well as connect the subsystem to the base structure. Our mounting and rotational mechanism fully considers customer needs at the beginning of the design and quantifies them to ensure that all needs met in the final product. Our design is a satisfactory level of tracking error. Each panel can rotate freely in 2 axes. No reflective area is shaded, and each panel moves independently. The CPVC pipe not only serves as a support structure for the servo motor and assembly, it also connects with the base structure. The maximum bending stress of the CPVC pipe was analyzed during design to ensure that failure would not occur. Through the wind data of the panel, vertical and horizontal forces were quantified. Using these values, the bending stress of the CPVC pipe was calculated at the contact point with the base structure. Dividing the yield strength of CPVC pipe by this calculated bending stress, the factor of safety was found to be above 2, which satisfies customer needs.
The rotation of the panel is done by the servo motor. Therefore, it is necessary to choose a suitable steering gear to minimize the cost while still satisfying customer needs. There is a rotational ratio of 1.5 between the servo arm and the small U-joint connecting the push rod. Given that the minimum torque requirement of the servo is 1.35 kg/cm, the MG90S servo motor that we've selected can meet this requirement. In addition, at a rotational ratio of 1.5, this servo allows the panel assembly to have a plus or minus 0.24 degree error, which is below the 0.25 degree requirement.
The base structure we designed is composed of CPVC pipe and multiple 4-way pipe fittings. The control box is fixed on the CPVC pipe by 2 M2 screws. In order to secure the base structure, the bottom of each pipe fitting has a concrete base, which will be buried in the ground to hold the entire heliostat module. The base structure features a CPVC pipe that is the same size as the rotational mechanism, which reduces procurement costs. In addition, the sealed pipe keeps the wires safe from pests and weather damage due to the press fit attachment method. During the design phase, we made the realization that the area on which we install our module will never be perfectly flat. To solve this issue, the length of the CPVC pipe connected to the concrete can be adjusted according to terrain requirements to ensure the correct placement angle. Our base structure fully considers customer needs at the beginning of the design and quantifies them to ensure that all needs can be met at the time of design. Overall, our design satisfies the minimization of module area, selection of electronics, reflecting area ratio, and operating temperature requirements. Our design uses an ESP32 and level converter as the control unit. ESP32 not only has 16 PWM channels, but also integrates Wi-Fi function. Its small size and low power consumption made it the first choice for our design. Since the ESP32 can only output 3.3 volts, we use an 8-channel level converter to convert the voltage so that the servo can work properly. In this design, we assume that the input voltage is 5 volts, So the power of the servo will come directly from the power supply instead of the ESP32, which will reduce the working pressure and heat generation of the ESP32.
So in general, our Heliostat design can basically meet customer requirements in terms of module reflection, area, factor of safety, material cost, and service life.
The panel modules each sport a Mylar sheet that ensures high reflectivity at a low cost. These sheets are fragile and tend to crinkle or crease, leading to the addition of an acrylic layer used to protect and keep the Mylar flat. This inexpensive panel module was designed to allow for easy replacement, employing a press-fit grip attachment style, similar to that of a phone car mount. This is critical since the panels are only expected to last a fraction of the operating lifetime of the Heliostat. This allows for routine replacement, like an oil change, to ensure that the panels are consistently performing at their optimal efficiency. The movement of the universal joints upon the rotation of the panel is displayed in this short video. 3 universal joints are used in the manipulation of each reflector panel. These universal joints provide a free rotation angle at a low cost due to their modularity. They can be easily replaced, which allows for low cost maintenance. These universal joints are made of stainless steel, which provides corrosion resistance, high strength, and durability. And here we're playing it again.
Our utilization of servo motors is another unique feature that serves to differentiate our design. Servo motors are actually cheaper than other motor types, which helps to lower costs. Their inclusion in our design eliminated the need for external gears for Reflectile, which, considering the harsh installation site conditions, significantly lowers the probability of component failure due to gear damage from the environment. Another benefit of utilizing servo motors is that they are controlled independently of each other. This means that if a motor-related failure does occur, the rest of the module can still function properly. This feature serves to enhance the design's overall reliability.
Another key feature in our design is the material choice of CPVC for the base structure. CPVC, or chlorinated PVC, is very similar to PVC, but has increased strength and heat resistance. We feel this particular material choice was vital to protecting Reflectile from the extreme heat that can be experienced at the installation site. This increase in strength also serves to increase the design's operation lifetime. Compared to other typical support structure materials, such as metal or concrete, CPVC is relatively lightweight and inexpensive. This decreases the overall cost of the design. Additionally, the individual CPVC parts are attached using press fits, which keep pests and water sealed away from electrical components.
The cost of the Reflectile Heliostat module was broken down into 6 cost subsections. The first section is OTS parts, or off-the-shelf parts. This includes all parts that are purchased and already fabricated. The design consists of $58.73 worth of OTS parts. The second section consists of modified parts. These are defined as OTS parts that must be machined in some way. The cost of the modified parts totaled $25.62. Only $1.57 of raw materials and 45 cents of energy consumption were required in the manufacturing of each Heliostat module. Manufacturing labor and assembly labor required to build each module totaled $12.34 and $8.29 respectively. This leads to a total full-scale mass production cost of $107. This lies very close to the target cost due to our prioritization of modular OTS parts.
The Reflectile Heliostat module was designed with the customer in mind at every step of the process. Maintenance costs are low due to the module's completely tool-free installation and uninstallation. The highly modular Heliostat design allows for quick replacement of any parts designed to have a low operational lifespan, such as Mylar acrylic assembly, allowing the high efficiency and reliability.
So in summary, the Reflectile Heliostat module excels in regard to low maintenance costs, high modularity, and long operational lifetime. We would like to thank you for attending our presentation on the Reflectile and would love to answer any questions you may have about our design.
All right. Awesome. Thanks for that presentation. My normal practice is to let the panelists ask questions first, but there's one thing that you guys did right at the start that I wanted to ask about. So I didn't do it this semester, but in the past, I've actually banned the use of the word gator in any team name because it was, reflect a gator, gator reflector, solar gator, like just, and we actually, remind me sometime when we're not recording to tell you the story of how we got a cease and desist letter for Gatorade one time because a team basically called this was when we were doing the gate system for Warren Dixon. There was a group that called their team the Gatorade, which was, Gator aid, as in it was aiding patients to be able to walk on a rehabilitation machine. But we actually got a cease and desist letter for trademark violation. So you guys have got Reflectile, which is actually a very clever use of sort of a quasi UF branded word that doesn't have, Gator in it, which I really appreciate. I don't see a trademark symbol. So how are you guys protecting your intellectual property since you've come up with something that I would deem to be very creative?
So we are protecting it. It's just that we forgot to include that symbol in the PowerPoint. It goes into more detail in the IP protection section of our FDR. If you'd like to read that, or if not, I can explain it a little bit for you.
Yeah, no, please explain it because I'll read it eventually, but.
Okay, sorry, I think we're done. So basically, well, we came up with this design, and once we ended up with it, we were looking at it, and it was really great. And then we thought, could use something. We were already missing some protection, so we decided a logo would be a great idea, especially considering the fun name and the design and everything. So we landed on the Reflectile logo, and now we have that, and we need to submit it to the USPTO, and from there we can protect it.
Okay, and you guys are you're actively in the process of doing that.
Correct.
Awesome. Okay, good. And I have also an ulterior motive to ask this question because I was in the external advisory board, the mechanical and aerospace department's external advisory board today, and they asked the Mech 3 students that question, like, what are you guys doing to protect your intellectual property? And the Mech 3 students all sort of looked at each other and looked at me, and I'm like, guys, we did this in Mech 2. You should know the answer to this. So anyway, just want to make sure that you guys are taking active steps to protect your intellectual property. So I'm glad you guys are doing that. And I think that's a super cool name. So anyway, okay. That's a very minor non-technical thing, but I wanted to throw that out there before we turn things over to the panel. So panelists, it's up to you. Who's first to ask questions?
Let someone speak on the engineering part, if y'all don't mind, before I speak on the cost part, because my response to the cost may be reflective of how the engineering part comes out.
I don't know what we're gonna do, Julia. You always go first.
Well, then I will go ahead and go. Just FYI, so I very quickly did a search in Google for Reflectile, and there happens to be a Facebook page whose logo, at least the wording of it, looks very similar to y'all's. And I just put it in the chat. So just take that into consideration, that while I agree, y'all's is super cool. So there's been a couple people that have also thought it was super cool before y'all. You may still get it trademarked, but just know with it being very close, if they've not already trademarked, if they may have already trademarked it.
I was just going to say, I really appreciate you pointing out social media as a source, because we just went online and we're looking there, and obviously it comes up in Google searches, but usually Facebook isn't a, something that kind of clicks. So I appreciate you opening that up as another source to check for error.
Well, I mean, I literally just typed in Reflectile into Google and I'm actually looking at it right now. The first hit is on an Instagram Reflectile shop. The second hit is on a Facebook. The third hit is actually on Merriam-Webster. Interesting. So, oh, and then Fine Art America, Reflectile 3 framed print art. Oh, okay. So apparently someone has done art with that too. So just Google is your best friend. And
Yeah, we were
Google,
mainly.
that-
No,
Sorry, go
go
ahead.
Oh, I was just saying we were mainly looking at the patents that were already available, but
Yeah.
that's why I said I really appreciate you bringing that to
Oh,
light because it's
yeah.
kind of something that we didn't really think about as much as probably we should have is non-engineering related topics, right? So yeah, I didn't really, engineering
need to-
class, but obviously there's other things existing in the outside world, right?
Anytime anybody says something interesting to me, the first thing I do is Google.
It's a great idea.
So this is actually a good test of whether you guys remember anything from the IP section. So given that Reflectile already exists and it looks like it's in the public domain here in at least one or two other instances, how do you guys get your trademark now, given that somebody else has used the name? And it's still possible, but I'm interested in how you would do it.
So first of all, we would really need to differentiate ourselves from all these other companies talking about any art style. So I think you said it was an art company?
There's no, the first one, this Facebook is a shop in retail.
Okay, so like an Etsy shop kind of deal.
I guess so. I didn't look that far.
That sounds like that. And it also sounds like an Etsy shop kind of name. I actually have a couple of friends who try to do it. It all kind of fits together. So yeah, I definitely realize now that probably should have been something we'd consider. So to pursue this further, we would definitely want to differentiate ourselves and make it very clear that this is the patent for an heliostat module in engineering applications.
Well, patent and trademark are two different things.
I'm sorry, I meant and just related to the pursuing of a patent and a trademark,
Okay.
but I'm talking more about just the fact that differentiating.
Okay.
Yeah, there you go.
This would be trademark. Patent would be your Heliostat, your product.
Yes, correct. Sorry, I misspoke.
Yeah, okay. No, I figured you knew, but I was like, for
Thank
the
you.
sake of this being recorded and existing in infinity, let's do that. Okay, so yeah, like I agree with Dr. Trump. When I saw this name, I was like, that's actually a really cool name. I'm very impressed with whichever one of y'all actually came up with it. But yeah, take a look. It exists. Anyways, go to your cost slide for me, please.
Of course.
Okay, so this is why I was hesitant to go first. If your heliostat, I'm not an engineer by any stretch of the imagination, okay? So 80% of this presentation, I did not understand a thing, right? I understood doohickeys with thingamabobs. So if the engineering part of this is sound, and again, those would have to be everybody else on this call to weigh in on that part. If that's all sound, then your costs here are very interesting, mostly because I haven't seen anybody get even close to, hitting the target. I mean, we've seen some that are 5-6 times hitting the target. So remind me, so the full scale production, that would be if it was bulk costs. Did you guys have a cost of prototype?
Yes, we have the cost of prototype and the price will be $300.
Okay, that sounds about in par with this. And remind me, it's $107 per module or per square meter?
Per square meter reflective area.
Perfect. Okay. So yeah, I mean, again, assuming the engineering part of this holds up, I'm very impressed by the costs. Yes, it is a little bit over, but usually when you're this close, me as the investor, I can go back to my boss, I can go back to my company and be like, look, can we get a little wiggle room? Can we fudge it just a little? Can we make the budget work? So yeah, you didn't hit the target, and I appreciate that you mentioned, okay, yeah, we didn't hit the target, we're above it, but I'm cautiously impressed. Like I said, depending on the engineering side of this, because a screw is a screw is a screw. And, you know, I don't know an apple pie from a raspberry pie, from a what other type of pies there are. So, but from an outside looking in, this looks good. And then left field, sorry, totally taking a baseball hit here. I really appreciate that y'all dressed up, that you're in suits, that you look nice, that you sat up straight, you presented yourselves very well. That it really gives the impression that whether or not y'all have your act together in the background, you know, in the back of your heads, you might be like, this is complete chaos and I don't know what I'm doing. And I just want to like curl up into a ball and cry, right? Which is what 99% of us feel when we're doing presentations. But you don't portray that. Here, you're portraying a very professional appearance. You're portraying that you have your act together. And so that gives me more confidence in believing that your engineering part probably works just because you look like it does. So thank you guys. The only thing I would say is maybe in the future, look at everybody getting similar backgrounds. Or even, you know, with Zoom here, like my backgrounds is top 5. This is like a UF provided Zoom. You just go into your backgrounds and change it. So try maybe looking, you know, even doing, I would say get matching backgrounds if you can, just because again, perspective is everything. But if nothing else, do a fade background or something. But this is really just me nitpicking because the majority of this looks very good and I don't have anything else to say. So there you
We
go.
really appreciate the nitpicking. It just makes us very, are you sure there's nothing else that we could do better? I mean, we don't mind the nitpicking is my point.
I'm going to reserve anything else until I hear everybody else's comments.
Okay, thank you.
Mhm.
Okay, other questions?
If we have no more external members, I have a couple things written down. My first question is, I like that you have a panel mount that it's real easy to slide in and out, but honestly, what keeps it from sliding out? What holds it in? I mean, I know it looks like it has just 2 clips.
It's a combination of the clips, and then there's also a rubberized grip that is on top of the panel mount. So it's a combination of the press fit and then the rubber adding another layer of security to it.
Okay, so
In fact,
I might like to see so that, okay. Yeah, I sort of worry that like if you turned it, 90 degrees, that it would just tend to want to fall on out. I might like to see just a little something added to the design, like a clip that you had to, depress something to be able to slide it out. But okay, that is helpful.
Can I ask a question about that?
Yeah.
So would an alternative for fixing that to be maybe do some calculations based on the coefficient of friction to prove, like the coefficient of friction for the rubber tape to prove that it will stay vertically fixed? Would that help as well?
Well, you would also need to ensure a normal force on it. And that's going to be hard to do if you have to go close to vertical. You're going to have changing thermal conditions. So you're going to have changing normal forces on it. And remind me, what is the clip made out of?
I'm sorry, the actual like big metal piece?
The clip that's metal?
Yeah, sorry, it's stainless steel, yes.
Wow. So you did all this and met the price with stainless steel for the holders?
Oh, I'm sorry.
Wow.
No, I'm sorry, that's sheet metal.
Okay. I was like,
sorry,
really
I said metal out there, and then I
floored.
was like, wait,
Okay.
she's totally
Yeah.
right. Performance nerves are definitely a real thing.
And part of me is, I've seen so many of these things, and part of me is just thinking, it's cheap plastic, just make a little tab depression thing. But yeah, I'm okay with that. I like the way when you were talking about your wind loads, you gave us the wind in miles per hour and translated it immediately into metric, which is what all your calculations have to be in to come out reasonable, because it's insane doing fluids type calculations and anything that's not metric. But the metric, meters per second isn't going to be that meaningful to your audience. You gave us the most important numbers in terms that were meaningful to us, but yet you kept everything consistent. I'd like to see a little more room in your resolution for error. So like the error you gave it was supposed to be plus or minus a quarter of a degree, and your resolution error is 0.24 degree, that's cutting it really tight. Yeah, I guess that's about it.
So we have some iteration of the design. So this is the final version. So in order to reduce the error, so the first thing we use is instead use the hinge to connect the push rod and the panel, we use a universal joint. So if we use a hinge, we will have the very large space between the push rod and the hinge. So which will greatly increase the error. So we just didn't use that. And so in this design, we assume that the only error comes from the precisely moving from the servo. So that's how we analyze this rotational angle error.
Yeah, that's true. Regardless, you're gonna have, I would be a little bit concerned about the backlash or the slop, but you're cutting it so fine, maybe you would do better with just like a slightly longer lever arm horn on your servo motor. That might, if you could bring your resolution down to plus or minus 0.1 degree, I hate just being so dead on close to your absolute limit. It just makes me a little nervous. Not that it would be that horrible, but I'd like to, be a little bit closer on that if you could.
Yes.
Just for this component, I'm sorry.
Particularly if there's an easy fix. So if it were just a matter of choosing a different gear ratio, so in this case, I would say maybe consider, instead of using that horn for your servo motor, maybe consider one that's 25% longer.
Yeah, we will think about that. And also during the design, we try to use a different type of servo to solve this problem. So we do have find other servo that can do much better job than the MG91. However, the price of other servo just too high because MG90S is at a very large number of productions. So that's why we can get our price very low. So since we already made like 0.24 degrees, so we will try our best to decrease the price.
Yeah. When you've hit the price target, don't mess it up. Good job.
Thank you.
Can I ask, you were just referring to this section. I think you said something about factor of safety. Were those okay? Or factor of safety for other mechanical features? Were those still within the proper, or were they too close to 2?
Me?
I could have sworn you said something about the factor of safety. You said the kind of tolerances, you're cutting it a little close with your customer needs. I could have sworn.
No. I wasn't talking about anything other than the resolution error. Is that you're cutting that really,
Okay, I think I was mistaken just because we were.
And I know you've done tons of error analysis where often, you start with the resolution error because you're always going to have that, but there's lots of other sources.
Understood. Thank you.
May I ask another question for the optical loss? So during the customer needs, I noticed that we cannot have about the tracking, the optical loss due to the tracking error, but also the optical loss due to the panel itself. For the 40% of loss, is that only for the tracking error, or is that must be also including the material loss?
I think Trump should answer this question. He's had the most customer interaction experience and has gone around and around on this.
Yeah, my understanding is that that 40% is associated with the angle accuracy or I guess uncertainty in your ability to hit that angle. So this does not include the reflectivity of the mirror.
Okay, thank you.
And maybe I should say, I've seen this interpreted a number of different ways. I've seen it interpreted as like plus or minus half a degree, where it's, you know, really not. And at least you're being more conservative on your interpretation, and that's good.
Yeah, I should mention so up until this semester, it was plus or minus half a degree. And then in consultation with the customers, they actually wanted to dial it up or down, depending on how you look at it, make the requirement more stringent. And so they, between fall and spring, they actually changed that number from plus or minus 0.5 to plus or minus 0.25. And you can imagine, I mean, you've seen them doing the targeting tests in the lab, right? And the plus or minus 0.5 targets are those, they're maybe like 2 centimeters in diameter little circles. So now we're talking about hitting something that's like the size of a quarter from like 3 or 4 meters away, right? I mean, it's the level of accuracy that the customer is demanding is surprising, but that's what they need, right? If the mirrors stray too far away from that specification, especially over long distances, right? We're talking about a 100-meter tall tower with the farthest heliostats being 100 meters from the base. So what is that? That's 100 times the square root of 2, right? For the hypotenuse. If you're off by just a little bit, your sunlight basically misses the tower altogether. And then, you know, birds die and airplanes accidentally get hit with concentrated sunlight, and life is not good, right? So it's important to hit that specification, but the level of precision is very surprising. It's when you actually see it in you know, physical representation like we have in the lab, it's surprising like how little leeway the customer has given us. So, I just got a reminder from my email system that we've got to jump into the next presentation, I think, which starts in right now, actually 4:45. So probably a good time to stop. So let me hit the stop button. Let me find the stop button.